Okay, so we can start now. So, morning everyone here in Seattle, afternoon and evening to our international attendees, and to almost afternoon to my East Coast colleagues there at Ornell. So our session is on advancing earth science with artificial intelligence, transforming data into action. This is probably the most talked about topic for any of our earth science conferences that we have been visiting in the past year or so, right? So before we start discussing more on what can we do with AI in earth science, or how can we use AI for earth science data, let's wake up, I would say. I'm not a morning person, so I thought we can have some Slido polls to wake ourselves up. So just for me to know you all, how familiar are you using artificial intelligence or machine learning in earth science? Nice. Awesome. We have a good mix of expertise here in this room. Okay, online folks, are you able to see the Slido polls? Are you able to access them? Awesome. Thank you. So we'll move on to the next question. So we'll start off with a few Slido questions just to wake ourselves up and get in the groove. So which of these earth science areas do you think AI can have the biggest impact on? Climate modeling, we start off with it. So ESIP is the data conference because, like in most of the conferences, we won't see data product generation and metadata automation as the first focus for AI in earth science. But in this, we see that. So, that just tells the domain expertise of our attendees here. Okay, awesome. Then the next one, what most interests you about applying AI in earth science? Thank you. And we go to our starting. So in this session, I will provide you with an overview of some of the AI applications that the big earth science data players like NASA, NOAA, USGS, and DOE has been working on, and some from the private sector. Academics in the universities have been using AI in earth science for a while, just under different names of regression, classification. It's just changing names now. And of course, like deep learning. So there is a ton of treasure trove in Google Scholar that academic research encompasses AI in earth science. So I'm not covering that, but this is more to get you an idea of where are we with AI in earth science data. So as you can see, NASA is building the Prithvi Foundation model in collaboration with IBM that's been used for land cover classification, flood mapping, wildfire burn scar detection. It's being developed by the NASA Impact team at Huntsville, Alabama. And the same team has also been using AI with BERT to automate their data management processes, and they have developed a GCMD keyword recommender. So if you have a data set and you want a keyword that needs to go with your data set, what we usually do is we have to go and look through all the GCMD keywords. Now through this AI enabled application, you can just find a GCMD keyword recommendation for your data set. And then there is the Earth Copilot that NASA has been developing with Microsoft to create an AI chatbot. Now we all are doing that, right, in our own domains, creating AI chatbots to make it easier to access more information about whatever domain you are working on. And then there are other applications of AI through the various science missions. It can be water, it can be terrestrial ecology, it can be precipitation, anything. So all these science missions, the science teams, the academic researchers, they have been using AI in solving various science questions. So that's what NASA's been doing, and then what's NOAA been doing? So NOAA's been uncovering whale songs in collaboration with Google. So I found this very cool, that they identify whale songs through acoustic data, and acoustic data collected over 14 years of time at 13 different monitoring sites in the northern Pacific Ocean. And along with it, it's summer vacation time for many families across the country. And we are all aware of dangerous rip currents along the beach. So NOAA is working on providing hourly predictions of hazardous rip currents up to 6 days in advance. That's something very useful to the public. Again, so mapping urban heat islands, we all know what urban heat islands are, so NOAA has been helping with that. Mapping urban heat islands using both ground-based citizen science data, it's data collected by volunteers, and also through the satellite-derived surface temperatures. And then they have been identifying marine life with FathomNet. I wasn't aware of this either, so that's a new knowledge for me. It's an open source image database like ImageNet, basically, that can be used to train and test develop artificial intelligence algorithms to understand the ocean and the oceanic ecosystem. Along with it, we also have various teams working to improve the national water model, incorporating AI to enhance stream flow and flood prediction, and also water quality forecasting. That is something very unique that NOAA is working with, I think, University of Vermont. Moving on to USGS, I'm sure all of you are aware of how important critical minerals are now, right? So this is also something new for me, that USGS, in collaboration with DARPA, is automatically extracting features from old scanned geologic maps to help with the identification of critical mineral zones. And also USGS uses AI in its ecosystems missions area and earthquake monitoring, and also stream flow estimation through the Flow Photo Explorer. I don't know if you all have used it, but it's a very cool tool that it has, like time-lapse photos of a location, and then it uses AI to provide you a predicted stream flow forecast in that location using those time-lapse images. And then what is DOE doing? So I forgot to introduce myself. I'm Debjani Singh. I'm a senior scientist at Oak Ridge National Lab. It's a DOE National Lab. So what are we at DOE doing? in the AI for earth science realm. So DOE had this called AI for ESP, which allowed the public to provide or to come up with various ideas of how can we use AI for earth science predictions. And then we are developing Orbit, which is a foundational model for earth system predictability. And it is trained on massive data sets in petabytes from the climate simulations, from the various climate models, and can be adapted to various earth system modeling tasks. That is a very important focus for us at DOE. And then we also are developing science-informed machine learning for accelerating real-time decision in subsurface applications called SMART. And this is basically being done to monitor carbon dioxide storage and uncertainty in the quantification of that carbon dioxide storage in subsurface reservoirs during unconventional oil and gas operations. And then we also have a group named GeoAI in the National Securities Directorate, and there we use AI and machine learning for infrastructure mapping, change detection, damage assessment, population dynamics, and socioeconomic analysis. So, other than the federal big players in the earth science data realm, we also have Google, Amazon, Microsoft, and the other tech giants who are reshaping the earth science by embedding AI across their entire geospatial analysis stack, as we all know about them. For example, Google DeepMind's Weather Lab, then Amazon's Sustainability Data Initiative, and Microsoft's AI for Earth. Now, this is just a broad overview to all of you of where AI is for earth science data. And so in this session, we have the following presenters. So I will be presenting my research on AI in earth science data, followed by Drew Snuffer, who is going to present his work on ocean data. And then we have two online presenters at Oak Ridge National Lab, Zach Medley and Clinton Stipek, and they will be presenting on their research. Okay, so before we head off to the talks, another wake up Slido question. So what's one word that describes why you are attending this session? Just one word. Okay, so curiosity is the driver for us everywhere, I guess. I'll go to the next question. So you don't have to be on this. I'll go ahead with my talk, but if you want to rank the following barriers to using AI in your field, so you'll have access to these questions, right? So you can refer to that while we keep moving with our talks. Okay, so lack of training or expertise seems to be the dominant factor, and then funding or institutional support is the next one. It's good to know, and with changes in the administration, number two has become the most dominant for many of us. Okay, so here is my work. I applied artificial intelligence to extract and classify environmental mitigations from hydropower licenses. And thanks to my colleagues, Tom Ruggles, Arjun Bhattacharya, and Hong Joon Yoon at Oak Ridge National Lab to collaborate with me on this work. So before we go into the nitty-gritties of the work, I just wanted to let you all know that HydroSource is another data hub for all hydropower-related data. It's funded by DOE's Water Power Technologies Office, and it's the most comprehensive and the most unique national energy water digital platform that will provide you with all hydropower-related data to make your data-driven decisions. So if you work in the hydropower domain, please visit our website and explore the data sets that we are providing, the data sets and also the tools and maps that we are providing. So hydrosource.ornl.gov, we have various data sets, and we also have a data model that provides you with the interconnection between the various data sets. And as you can see, we have different types of data. It varies from data on energy, water, environment, socioeconomic, and hydropower resource estimation. So one of the data sets on that HydroSource digital platform is the hydropower mitigation database. Now, what is hydropower mitigation? I don't know if you all are aware, but when a hydropower plant or a hydropower facility comes up, it needs to be licensed. So if it's a non-federal entity, then it has to be licensed by FERC. And FERC is the Federal Energy Regulatory Commission. And so to get the license, the hydropower developer has to go through a lot of questions that FERC wants them, to be answered for regulatory purposes, right? So what happens is the license documents, are very long. It's 150 pages or maybe longer, and it has all the associated regulatory jargon in that document that you have to read through to understand that what is it that FERC needed to get us that license. And in that license, we have this mitigation records is what, if there is a hydropower plant that's going to come up here, what are the mitigations that the developer has to keep in mind to have that plant developed so that it is not environmentally harmful to the people or to the environment around. And what happens is you have to read through all of them manually to find out, what the mitigations are associated to that. So back in 2013, what ORNL scientists did was they read through all the FERC licenses from 1998 to 2013 and identified all the mitigations that are associated with each of the hydropower facilities across the country. And that data set is now available as a Microsoft Access or an Excel format on HydroSource. And I just want to point out that it was a time-consuming manual work over 2 to 3 years to go through all of those licenses by somebody, And this is the schema for that mitigation database. As you can see, that there are different tiers of mitigation. Means, let's say hydrology is the main tier, and then amongst hydrology we have water quality and this. So we came up with this nice schema of different types of mitigation. So the main mitigations were fish passage, hydrology, water quality, biodiversity, habitat, and recreation and cultural. And then there were tier 2 and tier 3. So we came up with this nice schema so that we could associate the mitigations associated with hydropower with one of these variables or attributes. And this is just to show you the distribution of the hydropower facilities across the country, and there are some which are federally owned and they're not FERC licensed, and the ones which are, and then you can see the ones which are the larger ones in capacity and the smaller ones. So this is just to give you a spatial idea of where our hydropower facilities are. And this is the distribution of the mitigation categories across those hydropower plants. Now, this is driven by the data that was collected manually by reading all those FERC licenses. So what we did for version 2 is we used AI. And how did we use AI? So instead of reading through those licenses, like 150 pages long, and it's not only the length or the time consumed, it is also biased by the person reading the document, right? I may understand, because the jargon is very different, so I may understand mitigation in one way, you may understand mitigation another way. So there is a variability in identifying the mitigations and also understanding them. So what we did is we used AI to help us in compiling all those data from the various licenses, as you can see. And we kept the same structure, almost the same structure for the second version with the first version. And what this helps us, so this is the new data set that we have on HydroSource. You can download this data set and use it for seeing how the mitigations has varied spatially, just like the map that I showed you earlier, that was for the version 1, and this is for version 2. You can do the same thing. And then this will help policymakers to explore the relationship between some of the mitigation measures and the various environmental indicators for those facilities. So as you can see, this is the version 2, which shows you, like how mitigation has been varying across the major HUC regions. So I'll go now into the method. So that was giving you an overview of what that data was. So as you can see, environmental measures, so it has, the FERC license has a lot of information, so we were just focusing on the mitigation for that work. Now we are going to, in the future, we'll focus on a lot of other things too. So what we did was, we first, so the version 1 data set was actually from 1998 to 2013. So what we did was, we took 2014 to 2017, all the FERC licenses, and then we read through each and every license, and we annotated the mitigations. Like we had to create a training data set. So that was our training data set. So we, one person read through, and another person QA/QC'd that to see that, like there is not much there was a variability, but not much variability. So we have a training data set from all the licenses between 2014 to 2017 that we created. And so it was, again, manual data mining, but we have to do manual work to develop our training data set for AI to work on, right? And I'll just go a little bit faster. So as you can see from each of the sentences, we picked up on the mitigation. So it was a very, very manual work. And then from those, our data set is providing you with all of this information. So what we used to do is, now we developed that training data set from 2014 to 2017, and then we used the BERT, the bidirectional encoder for, I forgot the R, but it's a transformer. And then we used it to detect and classify. So what we did was, we had the training data set, so we picked up the license for, say, 2018 to 2023, and we used BERT, or it's called a natural language processing model, to go through those licenses and see that if the mitigations that BERT is picking up was part of that training. So the training data set was driving what BERT is picking up for the licenses from 2018 to 2023. And then we allowed BERT to classify and also first to detect that if this is, like the paragraph that BERT selected, and then if that paragraph contained any of the keywords that were part of that training data set that we had, and one is the detection, and then we allowed it to classify into the mitigation categories that I showed in one of the first slides, all those 5 tiers, means all the tier 1, tier 2, tier 3, so we classified. So we allowed BERT to classify the mitigations that it picked up from the paragraphs into the various classes. So we continued this for each and every license and kept on refining the model because it didn't start off well because our training data was not very long. So it was just from 2014 to 2017. And once we did 2018, we added that also to the training data. Then we did 2019, we added that. So eventually we kept on iterating between training and testing till we had a continuous data set from 2014 to 2023. What we did was we went back to the old data set that was manually done, and we picked up a license from 2013 and passed through BERT to see, like how much of BERT is accurately classifying and detecting the mitigations versus what was already done way back in 2013. And we realized that the accuracy was pretty accurate. It was not 100% accurate because of course there's going to be human error, but the accuracies were very, very close. And then what we did was, when we did this, then we went back to have a continuous, now we had 2 data sets, right? So from 2014 to 2023 was developed by AI. And then we had this manual data set, which was done by manual data mining from 1998 to 2013. And we had to combine both of them, but because the algorithms were different, one was human done, one is AI done. So what we decided was, we decided to have a 1998 to 2023 all done by AI. So we took all the licenses that were issued during 1998 to 2014 and ran it through our BERT model and got a continuous data set of hydropower mitigations from 1998 to 2014. And here are some of the AI jargons for accuracy and for our training, validation, and testing data. As you can see that we had almost 90% accuracy, so it was not bad. It could have been better, but that's the best we could get. So then what we did was, now this is a continuous task because licenses will be issued by FERC every year, right? Whenever a license expires, you again apply for relicensing. So we came up with a decision support application that will, once you have the document downloaded, just put it in the system. The system will read through the document, annotate the paragraphs that has the mitigation words or mitigation keywords that are in our training list, and then it is going to give out, like detect, and it will give you the accuracy for detection, and then it's going to just classify it according to the various classes. So there is no manual involvement in this whole pipeline or workflow now. So that is how we started with AI ML in hydropower, and now we are planning with moving on with LLM-powered database management. I'm sure you all are aware of how LLMs are changing our lives, our work. So we are planning to use retrieval augmented generation, or RAG, to extract whatever a user wants out of those FERC licenses. Because those licenses, I don't know if you have ever seen any of the license documents that are issued by the government. Those are just legal jargon. It's very hard for a common person like you and me to understand a lot of it and parse through the data that is embedded in them. So we want to use LLMs to parse through the information that are in those DocFork licenses and then provide the users with whatever information they want, just like the chatbots that NASA and Microsoft and others are developing. And this is the broad system architecture that we plan to implement. So if you want to, if you have similar ideas at your end, we are more than happy to, share our knowledge and collaborate on it. So that's it. If you have any questions, this was a very broad overview on our work, nothing technically deep, but if you want to discuss more on the, deep technicalities, I'm here, so we can chat offline. Okay. Yeah, sorry.
What exactly are you feeding the RAG, or can you feed the RAG for context?
Sorry, what did you say?
Oh, I'm sorry. My name's Josh Brinks. Hi. I was curious as to what you intend to or what you are going to feed the RAG to supplement for context.
So what we plan to do is, so this is something that we are just brainstorming on. So what we plan to do is, it can be, anything, any question that, the user comes up with, right? And you feed that into the RAG, and then, the RAG, I don't know how the RAG works yet, but then the RAG does what it has to do and then provides the user an answer.
Okay.
I don't know if that answered your question.
Not quite, but it's all right. I mean, maybe you're not there yet on what type of
We're not there
information.
yet, yes.
Like sample questions, like you come up with anticipated user questions and
Right.
answer sets, maybe
Right.
that's in the RAG, or I didn't know if it was just a dump of existing licenses or just documents, so it's better better contextualized with the specific topic or
Yes.
what we're talking about here.
Yeah, so we basically have to come up with the various questions that can be possible to ask, right? In the sense, we can't just ask random questions.
Are you going to have the LLM come up with the questions for you?
Well, then we are open to, hallucination,
Yeah.
right? So
Just curious.
So we have to come up with questions based on the subject matter experts around that, because we have a fair idea of what data is there in those licenses, right? Let's say, what is the minimum flow at this facility, or what's the precipitation that, annual precipitation at this location? So questions like that. So we have a fair idea of what type of data are in those licenses. So depending on that will be our first cut, is to have a list of questions that we feed into RAG. And then as time goes, add more questions and context onto it. Yes.
Hi. Could you talk a little bit about the prompt part and what that's looked like for how kind of your prompt engineering and any kind of not exactly guardrails, but constraints for hey, ants don't yeah, I guess kind of guardrails, give answers that are in this form or answers that only focus on that. Did you do that, and what did that process look like for you?
We haven't done that yet. So this is in the future. So this is our next step. So right now, what we have done now with NLP, natural language processing, and BERT is basically, extracted data and build the database. Now the next step is that use LLM right now, and then, try parsing through the information that we have through prompts and questions and context, and then provide the answer that is okay, so if you want to ask questions, you can always put in your questions in Slido, and then we can probably, yeah.
Great presentation. My name is Ryan Abbott from Elm84. I'm curious if you guys, so as part of that, building your database, I can imagine having built similar systems that you want to make some modifications, you might update your models. Do you have in place now, or at least some ideas of how you can continually improve that data, like kind of retraining or fine tuning, if you will?
Right, right. Yeah, so we started off with a very small training set, right? And then we added more and more data to make it, like more accurate. So at least of now, from 1998 to 2023, we have pretty robust, like database. But we think that the best accuracy is what we could achieve. We can't, like improve that more unless we again go back and do a manual QA to see and, like fix whatever we need to fix. But that's just a time-taking process. So we kind of came to this conclusion that the ROI for that is not very big. So right now, the database that we have is the best we can have. Now, as time goes, like in the next maybe 10 years, we have more data. So, like, again, we add more data to the training data set, and then hopefully, plus technology is also going to improve. So, like it's going to provide us with better accuracies. Okay, so that's all I have. So if you have any more questions for me or any of our presenters, feel free to, like put in your questions on Slido, or is there any questions from online speak? No. Okay, so I will. No, we have not explored that, but I will take your question to our development team, and we can explore this. That's a good suggestion. That's the whole purpose of sharing our research. Provide us with your feedback if you have done similar research, so that we can explore things that we did not explore. Thank you so much. Okay, so I will log out from here. Thank you. And I will let Drew. I'll stop my share here.
Okay, so you want to do a share then from, should I do this or?
Yes, you can do that, that's fine.
Hopefully this will work.
It's from the Google Slides.
Yeah, so then Google Slides. That's PowerPoint. Okay.
You just have to go to the folder.
Yeah.
Oh, it's a Google Slide. That's fine.
It's all set, right? Slideshow. And then from here, I do share.
This one.
This one, perfect. Okay.
No, it's not showing.
Oh, switch.
Okay, where is this? Oh, this one.
That's it.
Let's try one more time. Do you know how it shows up here? Should I download and see? Because this is a Google slide, so
This one?
that I know, that we did, but, okay. Oh, maybe.
As you wish, yeah. Quickly,
It is slide. I shared this. How this slide? Just try. This is Google Slides, so again, I don't know. Maybe share this. I think that will be the. No. I'm seeing why it's not coming up here. Can I just download it? That will be.
Yeah, if you want to download it, just download it.
Yeah, I think that.
Yeah, we are having some technical difficulties online, attendees, so please bear with us.
Hopefully everything should be fine. Yeah. Okay. Did I share it? Let me share it.
Share it to 2 spots.
Okay. Good. Yes.
Okay, so our next speaker for our session is Dr. Drew Snuffer, who is a manager of data analytics and quality at Ocean Networks Canada. So he can introduce his work more. So to you, Drew.
Thank you, Deb Johnny. Hi, everyone. Good morning. I hope you've been enjoying the session so far, and thanks so much for that great presentation. That was a very interesting overview of your work. I'm going to shift gears a little bit for a presentation on my team's work, getting a little more into the kind of a more niche problem, but then bring it back to kind of a broader invitation that I hope you all take me up on. So as Deb Johnny mentioned, I'm the manager of the Data Analytics and Quality team at Ocean Networks Canada, which is a University of Victoria initiative. And so I'm here today to talk to you about some of the initiatives we have. Oh, and in the session link on Sketch, there's a Drew Snoffer as a presenter. That's an imposter. I don't know who that guy is. This one's mine right here. So we'll try and get that fixed. And so if anyone wants to reach out to me, you'll have an opportunity. I'd like to start with the land and sea acknowledgement of the Lekwungen, Songhees, and Esquimalt peoples on whose traditional territory the University of Victoria sits and where I'm privileged to work. I'd also like to acknowledge the Duwamish, Squamish, and Stillaguamish and Muckleshoot people for the host of this, for the privilege to present on their lands today. So just a quick roadmap here. Just going to go through, talk about Ocean Networks Canada and my team specifically, talk a little bit about the challenges we're facing, show a case study for you, wrap up, and then that invitation that I mentioned. So Ocean Networks Canada is a significant effort going on, undertaken in Canada to produce or to outfit the oceans with significant real-time inventory of, or infrastructure rather, that gives us real-time data. So we're in the Pacific, the Atlantic, the Arctic, and now even in the Southern Oceans in Antarctica. It's about a 650 million Canadian investment, and it's a non-profit government-funded initiatives. We have a little over 12,000 sensors that we've put out, a total of about 1.8 petabytes in our archived, in our data archive, which are all open, 300 data products, and 37,000 data users. The people of the organization include 34 Indigenous communities that we partner with to help us bring all these data in. We have about 170 staff and co-op students. So this is kind of a map of where we are. The majority of our infrastructure is on the West Coast, in and around Vancouver Island. The original infrastructure that was put into place include the Venus and Neptune observatories, and from there we've expanded out, doing coastal observatories, community fisher programs. We have buoys in the Arctic, and we have a buoy off the coast of Antarctica right now as well. quick note about my team, we have 11 data specialists. It's a very wide range of instrument and data types. We check the instruments before they go out. We monitor the data quality, the continuity and quality as they're coming in. We troubleshoot on any issues, anomalies, and we also try to find features of interest. In addition, we're also responsible for data products. The number of instruments that we manage and the amount of data that we manage just continues to grow, and our team cannot keep up. So the question is, how do we handle this? So the case study I'm going to bring forward to you today is on hydrophones. This is a hydrophone we have deployed at about 1,200 meters at Cascadia. As you can see, it's got 4 different hydrophones. It's an array. The colorful little socks here are basically to keep debris out and also prevent noise from the current. So those arrays, each of those hydrophones actually bring in continuous audio data. It's one of our biggest sources of data in volume. From that audio data, we can create what's called a spectrogram. The spectrogram has frequency on the y-axis, time here on the x, and then the power spectral density, which is basically how loud is the sound, represented by the colors. And so like you can see in the lower frequency here, we have a little more power, kind of midway through, not as much, and then further up, a little bit at higher tonals, we have some of those. I should mention this is 0 to 12 kilohertz if anyone's interested. If you're looking at this, even as a non-trained specialist, you can clearly see there's a problem. So we have this temporal dropout for a period of time. It's not super long in this one. It's just under a minute. But we have to, as my team responsible for the quality of these data, we have to annotate or flag, or in this case, annotate, since it's a complex data type. However, with our large network, this takes a lot of time to go through manually, and was taking about a half of the time of one of our most senior data specialists up until we began this initiative. The solution we've come up with is to create unlabeled data learn from unlabeled data to get supervised tasks for the data itself. So this is a self-supervised learning approach. Essentially, we can create pseudo-labels using this process to create a pre-trained model. So I'm not going to go too far into the details of this, but just to give you a bit of a sense of how we're going about this, this is following self-supervised audio Mamba, which is a algorithm developed by our friends at Columbia. Essentially, what we do is we chunk up these spectrograms and mask out certain sections. They run through an encoder, and there are 2 steps here. One is the algorithm. It looks at reconstructing those pulled out spots, as well as the location within 3x3 area. So we have both representation, the ability to reconstruct the signal, as well as the location of features of interest. The second step is kind of a more traditional neural network that allows it to set the weights and biases, preset the weights and biases, and from that we can get take it into a binary classifier. Right now it's just saying, is there anything there? The various classes of things that we might want to detect besides errors include things like rain, ship noise. We're beginning to look at volcanic vent collapses at Endeavor, and potentially even doing some whale call stuff as well. So it's pretty exciting stuff. So this is all under a project called Building Bridges. I'm going to shift gears just a little bit, or talk a little bit about some extension work that we have. This is an ADCP, for those of you who aren't familiar, acoustic Doppler current profiler. It basically gives you currents up through the water column using 4 transducer heads that allow you to constrain the velocities at the various depths. And this particular ADCP We have a visit by a friendly octopus to his friend, the snail, who has taken up residence on top of one of the transducers. So as you can imagine, this creates some issues as well. So if we're looking at a visual representation of the ADCP beam intensity, you can see when the snail is sitting there, there's a problem. This is not actually from the snail, but this is a problem on one of the beams that we have. So again, someone could go through here and do this over and over and over. However, by extending the work that we're doing with the two-part approach with the hydrophone work, we're beginning work now on doing automatic detection of errors and data issues in ADCP data as well. So we're still working on this. Here's just a quick summary using the algorithm that we've developed. An annotation and prediction can be applied at what is visually a correct area. So where we are today, we're basically a pretty talented team. We're challenges with our workloads like everyone. We have a mix of skill sets, some people with a fair bit of AI ML experience, others with less so. We have a lot of time-tested processes, but those do not scale. So we're working on building our skill sets using more state-of-the-art techniques by doing basic online training, strong support of each other, and then it's also important to address the cultural change aspects necessary to begin to incorporate new technologies like this. So finally, the invitation I promised you. This work is part of the Building Bridges initiative. It's an effort funded by the Ocean Supercluster in Canada, and we are seeking to create a community of practice around ocean AI, which doesn't really currently exist as much in Canada. So the invitation to you that I'd like to make today is to please join us. This is our just an initial organizing page that was put up by our friends at CUS Atlantic, along with a code or a web link, and then there's a code. Feel free to check that out. We'll have a workshop coming up in October with a Canadian organization called MIAPAR focused on AI. We'll be doing a presentation of the hydrophone anomaly code that the code for the hydrophone anomaly detection, as well as some of the other efforts of the organization. So I'm not going to read through this, but I'd like to acknowledge my fellow team members, the Ocean Supercluster for funding this work, and Canadian Foundation for Innovation and Fisheries Oceans Canada, who support my organization. Thank you.
Questions for Drew? And online attendees, you can go back to the Slido and put in your questions there, or you can use the chat, and we have our fellows to help with.
On one of your slides, you showed your kind of your workflow with the masking, and then two different tasks, one kind of decoding and the other classification. And I was wondering, is the decoding the part, which I think of kind of like in my applications, like gap filling, or I'm trying to deal with, problems in my data. But I wonder, like, for your applications, what is the decoder application used for, or why are you doing that?
I think hopefully everybody heard that online. So essentially the encoding and decoding is a way to look at a representation to train the model. So we take out some patches from the spectrograms, and then we ask the model, fill it in as much as you can. And so that trains it. And so that prediction then is compared with the actual value, and we minimize the error on those patches. That both in terms of the contents of the patch as well as the location of it within a certain area. So the encoding is creating the weights and biases. The decoding is creating the prediction of what's at that spot, and then we minimize the error with the actual and the predicted. Does that answer your question?
I guess my question was, is that important for your classification task? Or do you have another application where you need to be able to predict gaps in the spectrogram? Like, do you have missing data that you have to fill in? Or is it needed for the classification step?
We don't fill in any data. All the data that you would download from the portal are actually data that we've collected. There's various ways to fill in data, of course, and it's not for filling in. It's strictly for pre-training. That's step one, that then goes on to identify where there are issues in step two. And then from there, we would create an annotation saying this is an issue, but it allows users to at least kind of pull out those types of things. And I'll also note part of this effort is involved with creating annotations that are machine readable, AI ready, so that, we can find those annotations easily, and then people can choose to keep them in or pull them out, depending on their own applications.
Thanks, Drew. One more round of applause for him. Okay, now we will move on to our online presenters. Zach, you're up next.
Yes. Would you like me to share my screen
Yes,
for my presentation?
yes, please. If you can do that, that's going to be easier.
Okay, perfect. Oh, I'll have to send a request. I just sent the request.
Yeah, we have,
I don't know who manages the permissions.
yeah, we have Jill and Devashish over here. There are two fellows who are helping.
Okay, perfect. I think it'll work now. I just got a notification. Oh, wait, wrong button.
It's still not?
Oh, no, it'll let me now. I just clicked the wrong button. Can everyone see my screen okay?
Yep, you're good to go, Zach.
Okay, perfect. I'll go ahead and get started.
Yes.
So, hello everyone. My name's Zachary Medley. I'm on the metadata team at the ARM Data Center. And today I'll be presenting my work on generating data product descriptions using RAG with an LLM. So before I get too deep into it, I'll give a brief outline of my presentation. So first, I'll introduce what ARM is before introducing the project itself, then going over the scope and division of the project, before giving a brief conceptual background, then going over the different components of the project.
Jack,
Oh, yes.
just give us a second. I'm trying to share this, your screen in our
Oh,
room.
was it not sharing?
It was shared on your end. I'm just trying to put it in our room. So just give us a
Oh,
second.
okay.
What's the screen options? Jill, can you ask Alicia or someone to come? Yeah.
Hold on, Zach, we're having some problems here, okay?
No worries.
Zach, I appreciate you being the guinea pig for me before I do my virtual presentation.
I was about to say, I was the one that went first for virtual.
It's always kind of scary to go first with a virtual one, so I appreciate the fall on the sword for me.
Sound fine.
Right, we had issues with in-person too, so yeah, so we are working through all the challenges.
Yeah. Maybe let someone come.
Yeah, she's here.
Yeah, how do I pull the online presentation here? He's presenting from his end. that I'm not able to find that screen switching.
And it's been working this entire time?
Yeah, I mean, if we present from here, that's fine. But if someone presents, he's handling everything from his end. So how do I switch everything? It doesn't show up there. That's what I'm asking. I don't see an option here, so. Because, yeah, I don't see anything here to.
So do you want us to drive it then?
Oh, wait. Wait. Can I? No, this is not the one. No, this is not the one.
I haven't seen this happen before. Because everything I thought shared would show up here.
Yeah, it's not happening, so that's why I'm a bit. Oh, wait, by the way,
What if I tried unsharing then resharing?
yeah, can you try that? And also, while you're trying to slideshow, there should be an option of duplicating the screen.
For the slideshow or for the,
For the slideshow, if once you,
okay.
yeah, you should see an option of display settings.
Wait, can you see my screen now?
I can, but
Okay, perfect.
yeah.
But we can only see it on the computer, but not on the big screen in the room. So that's what
Understood.
like, yeah.
So you said when starting slideshow,
Yeah, go to slideshow and then you should see it's the south one. Yeah. This should be.
maybe it's under the,
No, if I share it, then he won't be able to.
Yeah, that's what, yeah, I understand. I don't know why it is happening.
No, it should directly show there, but I don't know. There's some settings.
So like something like disconnection is.
No, they should be switching. I am not able to find that. If I try this. Let's try. Just should I? No. Let's try something. Yeah, thanks.
No.
I think it's something related to display. I think we need to check the computers.
Yeah, go to settings.
Like here.
I have no idea.
I know.
Do you have it? Then it
There
should.
must be monitor or something.
No, it should be. No, it's not related to that. Oh wait,
Oh, that's just identify. Duplicate.
can you select two?
Duplicate. No, now it's gone. Now it's.
Yes. Yeah. No, it's working. Wait.
Yeah. Maybe.
Yeah.
I think we can just
Yeah, Zach, I think we are good.
Okay, is it showing up now?
Yes.
Yeah. So you start from the beginning again. Introduce
Okay.
yourself, please. Yeah.
I can do that.
Yeah.
And I'll start my timer over again too.
Yeah, that's fine. That's okay. We are running over because we have all this, like difficulties, right? So don't worry about that.
It happens. Yeah, I appreciate you all having a virtual option too. I know adds a layer of logistics.
Yeah, sure.
All right, yeah, I can go ahead and get started again whenever you all are ready.
We are. You can go ahead, Zach. Yeah.
Okay, perfect. Hello, everyone. So my name's Zachary Medley. I'm on the metadata team at the ARM Data Center, and my project involves generating data product descriptions using RAG with an LLM. And so I'll give a brief outline of my presentation before I get too deep into it. So first I'll introduce ARM before introducing the project itself. Then I'll go over the scope and division of the project before giving a brief conceptual background. And then I'll give a breakdown of the different components of the project. Or I'll give, an overview of the different components. And then I'll go over the summary and broader applicability for this work. So before I go too far, I'll introduce ARM, or Atmospheric Radiation Measurements. So we are a Department of Energy Office of Science user facility, and we have over 30 years of atmospheric measurements across all 7 continents and 5 oceans. And so we have data dating back to the early 1990s. And our measurements are collected through both permanent instrumentation sites and hundreds of field campaigns. And I have a map of all of our sites and campaigns on the right of this slide. I'd particularly like to draw your attention to all of the orange points, because those are our permanent sites. And one of the ones we have is in North Alaska, the North Slope, Alaska site. We also have the Southern Great Plains site in Oklahoma, and the Eastern North Atlantic site off the coast of Portugal. And we have over 7 petabytes of these research quality measurements, which are available for anybody to use on our data discovery interface. And in addition to the data, we also have extra user capabilities, such as Jupyter Notebook cookbooks for data analysis, and computing resources for model simulations, support analytics, and machine learning applications. And now I'll give a brief introduction to the project. So we have over 8,000 data products currently visible to users with no accompanying natural language description. And users would benefit from a plain language description, which tells them more about what is in each data product. And there are many other data centers which have this. And there are also certain metadata standards, such as the CSDGM, which require a plain language description as a metadata tag. However, a human generating 8,000 data product descriptions would take an astronomical amount of time, which is why we opted to use an LLM for this application. And so for the scope and division of this project, so our scope is to use an LLM. We're currently using Llama 3 to generate plain language data product descriptions based on both metadata information and instrument handbooks. So for this work, we will first backfill the existing data products with descriptions after evaluating a robust sample. And then for the oncoming data products, so for the future ones, we will have a manual review process in place, although this would be impractical for all 8,000 of our existing data products. And our project is currently divided into 2 phases. Phase 1 involves generating 1 paragraph of the description based on metadata information from ARM's databases. And we've made significant progress on this phase. We are actually working on final edits and rolling this into production. And phase 2 involves generating the 2nd paragraph of the data product description to give more details about the instrument for the data product. And the work for this phase is still in development. And now I'll go over a brief conceptual overview of this project. So the first what I'll go over is RAG. And RAG involves supplying an LLM with retrieved information to use as context. So public LLMs such as ChatGPT and Copilot will generate answers from pre-trained data, which may not be relevant to the application. And real quick, I just got a message that I'm frozen. Am I back yet, or? Oh, am I still on? I just got a message that I was frozen. Oh, you all can still see me? Okay, perfect. I just wanted to make sure. Okay, so going back to the presentation. So RAG is useful for cases with very specific and detailed domain needs for plain language text generation, such as data product abstracts. And RAG grounds the model in a set knowledge corpora, which in this case is ARM's database and documents. And I have a schematic of RAG. And oh wait, are you all? I just got another message from the. Can anybody in the room hear me? I know I'm good online. Oh yeah, I don't think they can hear me in the room. I just got a Teams message from Debjani. I should probably wait for. Oh yeah, they got disconnected on their end. So, sorry everyone online. I don't know how long they've been disconnected for, but I'll wait for them to come back and from the room. Clinton, you're presenting next, right?
That's the plan, yeah.
Yeah. I'm really glad they did the virtual option. It happens with virtual events like this with technical difficulties or hybrid events.
Yeah, it can. Definitely can. So yeah, just I guess patience is the best virtue.
Yeah. You're at Oak Ridge also, right?
Yeah, I'm at Oak Ridge. Are you presenting from your office right now?
No, I booked a room because I just have a cubicle. And so I didn't want everyone around me to have to listen to me talk the whole time.
It's good
I
stuff.
booked,
I'd want to listen to it anyways.
yeah, so I booked F-115. Are you part of DAC then? Oh, what part of Oak Ridge?
I'm in the National Security Sciences Division or Directorate, I guess. So I work in a group parallel to GeoAI, the one that Debjani was talking about earlier. So I work in a different section, but within that same division. Yeah.
Gotcha. Yes, I remembered you probably said it earlier, but I forgot in that time. I was too busy thinking about my presentation.
Yeah, no stress. I'm interested in this one though, because I work with regs quite a bit, so I've been trying to develop a few out for. They're awesome. I like them a lot. They have a lot of applications too, and it's insane the differences in accuracy you can get from a large language model that's publicly facing versus when you train it on some RAG infrastructure, and it's pretty fun.
Yeah, no kidding.
I guess while we wait for them, I had a quick question for you, Zach. For your document store, how are you guys storing that?
So we're storing the documents. We're using LangChain architecture.
LangChain.
So
Okay.
we're using a database table with LangChain.
Okay. And I'm guessing you're not doing any embeddings or anything, right? For your
Uh,
documents?
we aren't for the metadata descriptors. There's a second phase where we work with the instrument handbooks. And for those, we do have embeddings.
Okay, gotcha. Thank you.
Did you for your infrastructure, were you using PDFs and CSVs, Zach, or was it kind of a mix, or was it? I mean, I again, as I develop mine out, I almost have to build them out separately just based on the embedding issues. So I was curious what you guys are using, if you're using that or if you're using tabular formats.
We're using Tabular for the database, but for the yeah, we're using Tabular for the database, but then for the instrument handbooks, we're using PDFs. And we have different pipelines for each because they don't play nice with each other.
Yeah, that's what I'm finding out. And CSVs and PDFs, especially like tabular CSVs, like population metrics, right? Like they have that very structured information versus PDFs. It's like there's a sentence that says something. So I've been finding issues with the large language model being able to identify those. So it's fun to see though, because once you fine tune a reg, you can get those really minute things, segmented out.
So have you done fine tuning with your application too? Okay, gotcha. You said fine tuning. I just wasn't sure if you meant the fine tuning machine learning definition or just like fine tuning the pipeline.
Oh, good question. Yeah, no, I'm right now. I have I think 4 or 5 regs built out. I also use LangChain though, to be honest with you, and I've liked it a lot. And so when I implement that LangChain, it comes back with about 80% accuracy for a lot of the questions I ask. Because again, I'm using CSVs and PDFs, so I'm kind of going kind of minutely in there. And what I've found is that the PDFs, it works a lot better than the CSVs, and so CSVs I've separated out, right? So I'm going to fine tune that that reg approach on both of those once it gets to there. But
Gotcha.
it's fun too because it's such a broad domain, and there's so many different ways to do it. And I think the biggest issue is like you have all these papers, right? And they're all most of them aren't peer-reviewed publications, so it gets kind of tricky to like wade into those waters as well. But the large language models move so fast with this retrieval augmented stuff that you kind of have to be on your toes.
Yeah. And one issue I found too is that sometimes there's minor inaccuracies in our data or in the handbooks, which are then reflected in the abstracts. And so I'm like, oh, there's an error in that. But then it interpreted the source correctly, but there was an error in the source. I don't know if you've run into that as well.
You're probably a little bit ahead of me right now, it sounds like, but I think I'm not too far on your heels just in relation to like infrastructurally speaking. But it's kind of just a peripheral project for me, so I haven't really spent too much time like hands-on, but it's kind of like, when I have time, I'll look into it. For what I'm using it for, it's been working great. That's why I haven't had to go too in depth with what I need, like, those really minute, like nitty gritty things. But for the next application space that I am looking at, I will need to get into that nitty gritty space. It's going to be kind of tricky. So,
Yeah.
and it's fun too, because again, there's so many applications and domains that this can be applied to. So, did you go to IEEE Big Data? Have you been to that one before?
I have not. I almost went in December, but I'm actually not a trained computer scientist. I'm an atmospheric scientist by trade.
My
So-
master's is in marine ecology, and now I do artificial intelligence. So,
so you know, so yeah, you feel the same way.
Yeah. But last year at IEEE Big Data, every paper was like large language model with a reg, large language model with a reg, just applied to all these different domains. So it was pretty fun to see, because you do disseminate these very large data sets into manageable chunks, right? That you can actually extract valuable information from.
Have you heard of MCP any?
Yeah, I have.
Yeah, MCP is definitely taking off now, kind of like RAG was. Oh, I just saw Room 5 is the host now, so maybe that means we're about to be back in business.
Zach, we probably will need to restart again, but then we have to switch a little bit because Clinton needs to be somewhere earlier. Clinton Nagendra just texted me that you have to be at the intern presentation, right? So if you want,
I think
Oh, you can
I
go
think
first.
I think 20-ish minutes or so is fine. So
Is
Zach,
fine?
you can wrap it up, and I'll hop down there about 1:20. Yeah.
okay.
Oh, I barely started, so you should probably actually go ahead, if you don't mind.
That's just fine. I'll pick up the mantle.
Okay, so we'll let folks come back in because we let them go take a break is because, like our Wi-Fi over here just stopped working. So we couldn't do anything. It's the hotel Wi-Fi, right? So nothing is in our control.
10 minutes each, because after 10:30 is another session. Oh, it's 11. Oh, sorry. Okay.
I just checked that. Yeah. Yeah, very sorry. We have, we absolutely can't do anything about this.
It's not a big deal. I think all of us understand.
Yeah, it happens. We've just been chatting about our respective projects, so
That's nice. I was texting Zach earlier, and then now I started texting you, Clinton, so, like, it's kind of juggling around. But surprisingly, my laptop internet, the hotel internet was working. It's just that this room's, like, Wi-Fi, the PC, since the laptop here connected to the Wi-Fi was not working, so that's why you got dropped off. Right, that's something that none of us expected. And the funny thing is, it's an AI session, right? So we are all talking about AI. And the very basic Wi-Fi didn't work. Right, we went, we went back to the basics of rebooting the laptop manually, hard boot. Okay, I think we can start, so, with whoever is in here, so we have pretty good set of people. Yeah. Yes, so who's going? Zach, are you going, or Clinton, are you? We are fine with whoever goes.
Clinton, you should probably go so that you can get to the event. I don't have anything time boxing me.
All right, thanks, man. I appreciate it. Yeah, I can go now. Then that's fine.
Thanks, Clinton. Do
Do
you
it-
mind introducing yourself before you start? Because
Yeah,
then I don't
absolutely.
have
Yeah, no worries. You're
to
good.
switch back and forth, yeah.
No stress. Zach, how did you present your screen actually, by the way, though? I'm kind of curious about that to make sure I can do that appropriately.
So I shared my PowerPoint screen and not my entire screen.
Okay. Okay. So let me see. All right. All right. Can everyone see my PowerPoint screen?
Not yet.
Not yet. Okay.
Yes, we
Yes,
can.
we can.
Okay. Okay. Let me try to do presenter mode.
Yeah.
Okay. Not let me. Give it a second here. Come on.
And we're still seeing the chat box in the middle of the screen.
All right. Can people see my screen still or no?
It's coming up.
Okay.
Yes, we can now.
You can see it, and it's the presenter mode.
Yes.
Okay, wonderful, wonderful. Yeah, thanks everyone for the patience on this stuff. I appreciate it. So like Debjani was saying, my name is Clinton Stipek. I work in the Oak Ridge National Lab in the National Security Sciences Directorate. And I'm going to be talking about kind of leveraging artificial intelligence and machine learning workflows to kind of characterize the built environment. So it's a little bit of a change of pace, but the way we structure our workflows would be to agnostic of domain. So there's a lot of impact for urban heat islands, especially with mobile home parks or at-risk communities, especially in relation to flood risk hazards and things like that. So a little bit different from what the presentations have been so far, but still kind of, that artificial intelligence machine learning flavor to kind of characterize a different aspect and domain for further use case applications. And so as of now, oh my gosh, come on. There we go. Okay. Everyone can still see my screen. It's not frozen or anything. I'll take that as a yes. So currently populations are kind of exploding at a pretty unprecedented scale right now. And to address for that, the built environment's expanding. It's not just expanding in, Seattle, Washington, Dallas, Texas, or, Phoenix, Arizona. It's expanding at scale. We're seeing this especially in regions in Africa and Asia and South America, kind of agnostic of where you are located on a map. The built environment's expanding. This can kind of come up in many different forms. There can be, these tall, high urban skyscrapers in downtown core areas, and you also kind of get urban sprawls. again, similar to what you see in Phoenix or Dallas, Texas, or Phoenix, Arizona, or Dallas, Texas in the US. And it's not just important due to these expansions of the built environment, but it's the fact that more individuals are actually moving to cities and these urban environments versus these more rural communities. And according to the UN, about by 2050, about 68% of the population on the global scale is going to be living in these urban environments, right? And so the question kind of arises of, and it's important to note, like how do you track these changes? How do these changes happening? Are they happening at a local scale? Are they happening at a regional scale, continent scale, country scale, global scale? How can we kind of quantify these changes and understand better metrics to understand this, so we can track urban heat islands better? We can track energy efficiency of buildings better. We can track populations at risk in these flood zones and or these wildfire zones. And it's not just the wildfires, right? You also have to worry about the pollution in the air after the wildfires, things like that. So how can we kind of start to track these built environment patterns at scale? And so over time, over the last few years especially, there's been a huge expansion in open building footprint data sources to help kind of quantify these changes across the built environment. Microsoft comes out with theirs. Google has an open footprint data set. Oak Ridge also has one through USA Structures, sponsored through FEMA. That's a lot of work that a few individuals in my group have done. Taylor Hauser, who's one of my core collaborators and an amazing person, even better scientist. He works a lot with USA Structures. But when you really get into these footprint patterns, one of the issues is that Microsoft, Google, and FEMA or USA Structures here. One, they use different satellite imagery, right? Or they can. And then two, object detection varies from, Microsoft to Google. For example, Microsoft uses a DNN architecture, deep neural network architecture, versus, FEMA USA Structures use a convolutional neural network structure. And without getting too into the weeds, those are two very different architectures for a deep learner. That can lead to different results. So when you talk about object detection and object, anomaly detection, things like that, you can get very drastic differences. It's not just that, it's also the regularization for those objects, right? So Microsoft uses singular pixel detection versus Google uses a 3x3 sliding detection. So you can kind of delineate the buildings more in those core urban areas. And that's been proven in Africa at a scale for 100 meters, as well as building by building, between the differences in just the footprint patterns. So, me or Zach or me and Debjani could look at the same imagery for the same day, the same year, the same everything. And we could come back with very different depictions of what the built environment looks like from one algorithm to the next algorithm. And this is really important because when you use these algorithms that I'm going to introduce and talk about, these really depend on contextual features, the complexity of the footprint, and I'll show some images to kind of drive that home once we get into these later slides. And so now that we have all these footprints, we have all this information, right? We have almost, in India alone, Google produces 500 million footprints, right? So you also talk about scaling issues, right? And where data storage issues and things like that. But at the very least, there's been a lot of work to kind of contextualize these two-dimensional footprints, right? So if you think about that two-dimensional footprint in space, it's not 3D, it's not 1.5D. It's literally just this flat planar footprint in space, right? And so once you have that flat planar footprint in space, what can you kind of do with it, right? What's the point? How can we improve that and contextualize that? So this is mainly where Taylor's workflow comes into play. And this is for the USA Structures, that FEMA data set I just talked about. There's been a lot of stuff coming out of Europe with Bill Jecke and Milojic Dupont. Bill Jecke's at NUS lab in Singapore, and they do world-class stuff. It's really, really interesting built environment contextualization features. And then, these are kind of what some of them look like, right? You have your footprint area, you have your volume, if you have height, right? I'll talk about height in a second. You have the envelope area, the number of neighbors you have within context really matters too, and that's a pretty important one as well. And a lot of these are really interesting, and they contextualize the built environment at scale in different domains, right? So Milojic Dupont's used it for height. It's been used for age with Florian Nautikal et al. And so there's a lot of different ways that these can be applied to built environment targets. And the most recent one that came out was one by Hauser et al., this Gauntlet. This has just been recently open sourced. Most of the work that Taylor and I do, we really try to open source it. Neither of us like holding onto our algorithms tight to our chest. I don't believe that's, I believe in open science. And so if I'm using open footprint source data sets, I want to reproduce that for everyone to use as well. And so again, grab by the scruff of the neck and kind of pull back for 1 second, right? We have these unique footprint data sets at scale, right? cover global scale, country scale, continent scale. You know, anywhere you look, there will be some kind of footprint that you can leverage, whether that's open source or some just closed source, right? What we're trying to do is contextualize these footprints to answer, you know, multifaceted problems across domains. We're going from a two-dimensional platform into further built environment targets to look at. And so just a further deep dive into a little bit of the Gauntlet features. Again, this is kind of what you look at on a map in that top right. You just see these polygons, right? These two-dimensional polygons in space. And so what Taylor has done is he creates measures of geometric features such as the shape area of the footprint, the number of polygon or the number of vertices within a footprint. So you can see that something like this in this middle picture, you can see that 0.122. That's a little more of a complex shape versus if you look in the top left, that's just a circular shape, right? Just an oval, and that's just a lower score on that scale. And contextual as well have been really, really important. And so what contextual features do is you generate the number of neighbors you might have within certain set of radii, so 50, 100, 200 meter radii. And that's been really important in signifying a core urban area versus a rural area, right? If you take a Walmart footprint, sorry, Walmart's is the best example. You take a Walmart footprint maybe in, a rural area in Nebraska, or you take that same Walmart footprint in New York City, you're going to get drastically different number of neighbors. And so that's really helped to kind of delineate a core urban area versus a rural area as well. And again, that code's been open sourced. So in that bottom left, it's been interesting to see because we've had a few researchers reach out who use this for tree crowns. So they look at tree crowns and try to disseminate what trees are more susceptible to wildfire risks than other trees. And so the way we built our workflows is to be agnostic of domain, which is really important because then you can kind of apply this, okay, we're looking at the built environment. However, someone could look at urban wildfire risks and with using the same approach and the same data set and the same underlying structure and patterns within that data set. And so once we have that, we've taken these two-dimensional footprints, right? We have contextualized these footprints with things such as number of neighbors, what's the footprint area, what does the shape look like, things like that. And so we started asking questions, can we use these morphology features to further characterize the built environment? Can we use artificial intelligence, machine learning to kind of take these and learn from these underlying patterns to then look into these built environment targets that the current landscape is lacking? And so one of the first ones was Daniel Adams et al. And Taylor and Jessica Mole, another coworker here. They looked in Ethiopia to see, can we identify use types of structures using these morphology features? This is hugely important in population modeling, right? You look at, okay, is this a mixed use building? Is it a, residential building? Is it a non-residential building? Can we look at multi-classification for this building as well, right? So for energy structure, for, building use as well, and can be essentially important for, what am I trying to say? Climate modeling as well, right? Especially in relation to urban heat islands, right? You get these really tall, core multidimensional buildings. They may have shops at the bottom and then residential properties on top. Those urban canyons kind of form around those a little bit. And so it can be kind of, this can be hugely important for an application piece in that, but this is just an underlying structure to, again, add further context to the built environment. And again, it came back with pretty good model results. You can see 80 to 90% results coming back for identifying these differences in classes for the built environment. So this is kind of my bread and butter and my main workflow. So building height at scale, if you look on a map, building height typically is not available. There's some data from Microsoft, there's some data from Google at a gridded structure, but it's kind of piecemeal, right? It's not too consistent with where those heights are located. You can use OSM as well or something like that, but then you run the risk of, it's somebody just volunteering that information, so you can't really validate it, right? And so Taylor and I kind of got together and we kind of asked ourselves, can we, these footprint morphology features are scalable, right? We can generate these anywhere we want, and we can just use the footprints. We don't have to use any other ancillary information such as city structure, distance to water, any of these kind of remote sensing products that can be kind of complicated. We don't need to use any of those. So if building height's only available at 3% to 4% of global scale as of now, how can we improve that and further, enhance this ability to further contextualize the built environment? And so we got this publication out about 2 years ago now that showcased the workflow of using just this footprint-driven approach, right? And so, this is results in the United States. So there's Phoenix, Arizona, more of an urban sprawl type-esque. And you can even see that from space and from these footprints, right? You look at all these are, kind of your cul-de-sac, your typical urban kind of sprawl look. Albany, New York, this is more of kind of an older city that was built. And you can see like some of these footprint structures are hard for the model to pick out, right? If you look in that top right, it almost looks like a key. And in that key, right, it was hard for the model to predict that. We're just using morphology features. This building may not have very similar structures around it. And that's a caveat associated with this work, right? When you're just using one source of information, one source of data, you can run into some of these complications. However, on a whole, within 97% of our structures were identified within 3 meters air. So if you look at this 0 to 3 meters, that's the majority of what this picture looks like. And that's kind of what we were going for, right? Again, there were some caveats. I'm happy to talk more about this work, but we were able to take these morphology features and now we've been able to use it for use type, as well as building height, two kind of key and limiting factors whenever somebody's looking into a built environment research. And so when we compared against Microsoft heights, right? Microsoft has some heights in the US. We found that statistically speaking, our approach was a little more representative of the built environment as a whole. And this was just an example for Phoenix right here, but we looked across 10 different cities in the US. We've also done some further analysis in Japan, Europe, and also more cities in the US to kind of really vet the approval or vet the workflow and make sure it works out well. And it's turned out really well. And so again, I'll kind of go through these next slides, but this is another framework. This one's under review right now, but we were able to identify mobile home parks as well. These core at-risk populations, right? They suffer from, higher related risks associated with tornadoes. Their structures get washed away. They're more pertinent in flood zone areas is where they're built. Whether that's zoning issues or not, it's kind of up for argument, it sounds like. But we were able to actually identify what a mobile home park is and delineate that from the built environment. And you can see mobile home parks are really unique in structure, right? They have these elongated kind of almost like eye-shaped buildings. If you look at non-mobile home parks, this is just a picture of the built environment as a whole in the bottom left. And you can see those differences. And our approach of using these morphology features is able to delineate those at scale. So again, leveraging these artificial intelligence machine learning models to contextualize the built environment, we can use these agnostic of domain, which is really important. And these can be further applied to, more domains and more options and more workflows. So while we've used it for building height, mobile home parks, use type, morphology features, right? Those morphology features can then be leveraged for a bunch of other different things, such as, urban heat islands. We've started looking at that a little bit, flood zone risks for mobile home parks, wildfire risks. And these morphology features can also be used in, structure agnostic as long as it's a polygon. And so some of these next steps, as I told you, there's differences in footprint, object detection as well as regularization. This is one example. So you have a LiDAR footprint, which is kind of the cream of the crop in black. Microsoft is underlay that in green. And then you have a Oak Ridge National Lab footprint derived on top of that in yellow. And you're going to see the differences, right? So these contextual features are really important for the models, especially the gradient boosting models. TabNet and some of those other deep learners are able to actually, leverage these a little bit better and kind of learn. But at a whole, this is kind of what it looks like. And then you can see these are just SHAP metrics for, let me see what value is that, NCount 1000, sorry. And you can see that, speaking of contextual events, right? So this is just signifying that as the NCount 1000, which is that neighbor value, goes down, your model inference goes up or goes down as well, I'm sorry. So it's just a nonlinear relationship right there. So with that, I'll wrap it up. I'm thank you for collaborating with us on these technical issues. I apologize for that as well, for not being able to be there in person, but I hope this was helpful and beneficial. My email address is on there as well, so please feel free to reach out. And thank you again, Johnny, for the opportunity here.
You're very welcome, Clinton. Great talk. So any questions for Clinton online, in person? And if you have any questions, Devashish. You can also put it in the Slido, but we have one question here, Clinton.
Yeah, hi. That was a great presentation. Thank you very much. I wonder if you could address a little more about where the approach that you've taken has been highly successful versus where you're still sort of struggling a bit.
This is going to sound super preemptive and very arrogant, but we have not run into any issues so far with scaling it for the targets we have applied it to. With that being said, I will tell you some of the limitations associated with it. The mobile home parks delineates very, very well, right? Those footprints are very unique in space. Those morphology features are able to identify that really, really well. Now, when you get into tall buildings versus small buildings, right, they may show the same footprint shape in the same core urban area. But for example, in France, there's a height limit that you can build buildings at to 20 meters in Paris, right, or something like that. Versus Dallas, you may get that same footprint shape and you might have that building be triple, quadruple the size, right? So when tall buildings, especially, it gets really complicated to infer accurately. And it's kind of a data imbalance issue and a class minority issue, which we've published an ensemble approach on to kind of address for that. But when applying at scale, especially from country to country, you run into different patterns within the built environment that may not truly represent what is actually happening. So doing a subsection model where you kind of single out specific patterns within the built environment, that seems to work better. So it's a really good question, and it's a thought-provoking one, right? It's like, where's the limit to this approach, right? We're seeing it being highly successful applied across different domains. So example, the IMF, the International Monetary Fund, we're collaborating with right now to do an economic assessment in Africa, and it's been great. Like, they've been getting really good results back with the building height model. We also work with Northeastern University right now on energy modeling for buildings, right? How are these structures, which ones should we address first? How should we retrofit these buildings first? And which patterns in the built environment should we be looking out for? So it's been applied across a lot of domains. There's no way there's not going to be issues, right? There always is. There is no perfect workflow. There never will be. The morphology-driven approach at the data and building by building level seems to give us more information that we can then use to infer for better metrics. That's kind of how I would think about it. But yeah, that's a great question. I hope I answered it okay.
Yeah, that's great. Thanks for your talk.
Yeah, and I will pull on it a little bit, probably. So what about countries where we do not have, like planned development? Like, like especially in the third world developing countries where it's very unplanned and, the morphology varies, I would say, even within smaller pixels, right? So how do you deal with that?
That is the hardest possible question you could have asked me, so I appreciate it.
Sorry, I was just thinking from your answer.
Yeah, no, that's a great question. So one of the hardest parts is when you go from country Y to country X. Country Y has great data, country X has no data, right? What do you do, right? Do you just apply blindly? Do you try to think about, okay, like, here's these patterns that are emerging in this country X that we have no information of. Maybe we can use an unsupervised approach to find similar patterns in a like country somewhere else where we have training data. So it's all about trying to connect that dot of using a data-driven approach, right? I'm not a subjective domain expert in the built environment, I would say, right? I leverage these data-driven approaches. So for example, when that question comes along and I'm a population modelist in Brazil and we're showing this unprecedented growth in these, these lower lying areas outside of Sao Paulo, I would say, I don't know what the heck's going on, right? I have to go back and look at my model and try to find a similar pattern with the built environment in a, it could be an adjacent country or it could be a country in Africa. I don't know, but I won't know until I look at those underlying patterns in the built environment using an unsupervised approach.
Right. Okay. Yeah, makes sense. Thank you, Clinton. Any other questions for Clinton? No? Okay, I'll let you go. Thank you so much for agreeing to present virtually, and we enjoyed your talk, and thank you again. Okay.
Thank you so much.
Yeah.
Bye.
All right, I can start whenever you all are ready.
Right, so our final speaker is Zach. Hopefully we can complete Zach's talk this time without interruption. I'm so sorry, Zach, we kept on interrupting you. So if you can start at your end.
Awesome. Third time's the charm.
Let's hope so.
Yes, and thank you to everybody who waited and stayed for the presentation.
Thanks to you for, like patiently waiting through this whole thing.
Can everyone see my screen okay?
Yes.
Okay, that's a good start.
Awesome.
Okay, I'll go ahead and get started. So hi everyone, my name's Zachary Medley. I'm on the metadata team at the ARM Data Center. And today I'm presenting my work on generating data product descriptions using RAG with an LLM. And so before I get too deep into it, I'll give a brief overview of my presentation. So I will first introduce ARM, and then I'll introduce the project itself before going over the scope and division of the project. Then I'll give a brief conceptual background before going over the different tenets of the project. And then I will give the summary and broader applicability. And so for an introduction to ARM, or atmospheric radiation measurements, we are a U.S. Department of Energy Office of Science user facility, and we have over 30 years of atmospheric measurements across all 7 continents and 5 oceans. So we have data dating back to the early 1990s, and our measurements are collected through both permanent instrumentation and field campaigns. And the location of all of our data collection sites is shown in the map here. I especially want to draw your attention to the orange sites because those are the permanent ARM sites, particularly the one you see here in northern Alaska, the North Slope Alaska site, the Southern Great Plains site in Oklahoma, and the Eastern North Atlantic site off the coast of Portugal. And from all of these different sites and field campaigns, we have over 7 petabytes of open source atmospheric science data available. In addition to this, we have some extra user capabilities for our 7 petabytes of data. So we have a computing resources for model simulation, support analytics, and machine learning, and along with Jupyter Notebook cookbooks for data analysis. And now I'll give a brief overview of the project itself. So we currently have over 8,000 data products visible to users with no natural language description attached. And users would benefit from a plain language description, which tells them more about what is within each data product. And there are many other data centers that have this. And there are also certain metadata standards, such as the CSDGM, which require a plain language description as an essential metadata element. However, a human generating 8,000 data product descriptions would take an astronomical amount of time, which is why we opted to leverage an LLM for this project. Now, for the scope and division of the project, so the scope is to use an LLM, in our case, Llama 3, to generate plain language descriptions based on both metadata information and instrument handbooks. And the first thing we will do is backfill the over 8,000 existing data products with descriptions after we evaluate a robust sample of the generated descriptions. And then we will have a manual review process which we put in place for the new data products which become available on data discovery for users to use. And the project itself is currently divided into 2 phases. The first phase involves generating 1 paragraph of the description based on metadata information from ARMS databases. And we've done significant work on this, and we are working on the final edits and rolling it into production. And phase 2 involves generating the 2nd paragraph of the description to give more details about the instrument for the data product. And the work for this phase is still in development, but we have a pretty robust proof of concept, which I'll discuss briefly. And so the conceptual background for this project. So RAG involves supplying an LLM with retrieved information to use as context. So with public LLMs such as ChatGPT and Copilot, they generate answers based on pre-trained data, which may not be relevant to the application, particularly if you have a very specific and detailed domain need, such as, say, generating data product descriptions for a data center. And so RAG, in this case, grounds the model in a set knowledge corpora, which in this case is ARMS database and documents. And I have a brief schematic of how RAG works in the top right of this slide. And I'll also go over 2 methods that I used for this project. So I used prompt augmentation, which involves strategically changing the prompt to get accurate results, and few-shot prompting, which involves giving a few examples of proper inputs and outputs to guide the model in generating a response. And now I'll talk about phase 1. So as I mentioned earlier, phase 1 involves generating the first paragraph of the data product description based on our metadata information, which is stored in a Postgres relational database. And we have several metadata tags stored within these databases that we incorporate for the model. We, of course, have the data product name, the instrument which collects the measurements, the most important measurements collected by the instrument, more details about how we classify the instrument, the level of processing done on the data, where and when the data are collected, and a link to more information on the instrument itself, which will be rolled into phase 2. And now I'll talk about the prompt augmentation steps that I used for phase 1. So we structured the query very carefully to get consistent, accurate results for the different descriptions. And I have a sample query on this slide here. And so you can see that we first feed in the metadata information, which is pulled from our database based on the data product name. And then, based on the metadata information, we instruct the model on how to construct different sentences. And through all of our prompt augmentation steps, we used 4 general strategies. We sought brevity, conciseness, and we also accounted for specific errors that we found during evaluation and testing. And in some cases, we had a slightly different set of query instructions for the different scenarios. And so brevity and conciseness. So if extra details are included that are unnecessary, it would make the model less grounded and more likely to give extraneous information. And if there are vague or conflicting instructions, the model would be more likely to hallucinate or give undesirable results. And one place I want to draw your attention to for these 2 tenets is sentences 2 and 3, because we had to give a lot of instructions to get the desired results, but we were very careful with our instructions to make sure they were very specific and clear and would not leave room for the model to go off the rails. And we also accounted for some specific errors that we found during testing and evaluation. So for instance, the model was originally not including every metadata tag, which obviously we want all of them. And so I included a blurb to account for that. And then we also had some issues with capitalization errors for the model. And the reason for this was because we have some wonky capitalization patterns for the metadata information within our tables, and we did not want this translated to the descriptions. So we added a blurb for that. And then we had an issue with the model messing up metadata hierarchy. So at ARM, our facilities are part of the sites. And so we were sure to include specific instructions in the model, so it accounted for that properly. And then we also had an issue of missing metadata tags not being accounted for. So for instance, there were a lot of times where the instrument handbook URL was missing. And so if it was missing, we just didn't want the model to include it at all. And so we included specific instructions for that within our query. And when needed, we had slightly different query instructions for different scenarios. So for instance, if the data within the data product were raw or processed, we would want to indicate that separately to the user. And also, we would want to describe the measurements slightly depending on how many there were, whether there were none, 1 to 3, or more than 3. So with all of these considered, we had a different set of 6 query templates that we fed to the model. And in addition to prompt augmentation, we also used few-shot prompting. So now I'll discuss how we integrated few-shot prompting into our workflow. So one of the major issues we had in initial testing in terms of flow and quality of the abstract was the model being redundant with metadata information descriptors. And I included 2 examples of sample inputs and outputs related to this in this slide. So you can see with the second one, the primary measurement inputs, if they were first, second, and third boundary layer height candidate, we would want the model to condense the details and not write boundary layer height candidate 3 times, because that would make the abstract sound really choppy, which is why we included these input-output pairings to guide the model. And another issue that we had was the model handling proper English rules, which aren't always followed, such as making the word data plural. And so I included an input-output pair where we have the word data treated as plural. And for our evaluation method for the 8,000 data products, so to test this application, we first manually evaluated a sample of the most frequently downloaded data products. And I won't go too much into our sampling method except to say that we sought the most downloaded data streams from data products from our different instruments. And we ended up with 369 data product abstracts, which we evaluated. And these sample descriptions were used during prompt augmentation and few-shot prompting implementation to evaluate our different strategies. And the sample descriptions were also used to see if our evaluation methods flagged the correct descriptions. And I'll mention again for the future, we will have a manual review process in place for each of the new generated descriptions for the newly created products. But this would be impractical for the existing data products since there are over 8,000. And another thing I want to mention about our evaluation, our goal for evaluation is to flag the descriptions for manual review and not automatically make changes because we want more control over the quality of the abstracts. And so the checks we've integrated so far, we have a flag for repetitiveness of the descriptions, a flag to prevent certain special characters, and a flag to flag grammatical errors. And we're also exploring a couple more checks. So we explored a semantic similarity metric, which ensures that all the required metadata descriptors from the query are within the final description, and a relevancy checker, which checks the prompt against the generated descriptions to make sure all of the necessary data and details are included. However, we may not end up needing these two flags for phase one, since the model's been doing a very good job of ensuring all of the metadata tags are included with just prompt augmentation. But we will definitely need these for phase two, which I will talk more about in a few slides. And so I've talked about the project scope, the methods, and our evaluation method. You all are probably thinking now, how did the results turn out? So the results turned out pretty good. So for prompt augmentation, we augmented the prompts to correctly describe the site code and facility code hierarchy for the evaluated descriptions. You can see on the left here, this is before we used prompt augmentation, which this is the incorrect hierarchy described. And then on the right here is after we used prompt augmentation with the correct hierarchy described. And for almost 13% of the descriptions in the sample, they were missing an instrument handbook URL. And in the beginning, as we were doing evaluation, many of these descriptions included a line which said the URL as none, which obviously we don't want it to say in the final description. And in the most recent run, only 2 of the descriptions in the sample included this tag as none, which was a very small percentage. But still, for the remaining offending descriptions, would want to add in a step in the evaluation to check for these tags labeled as none, to fully get rid of them and make sure that's not anywhere in our dataset descriptions. And then for few-shot prompting, I was really excited about this result. So before we implemented few-shot prompting, over 18% of the descriptions were flagged as repetitive. Now, in a population of 8,000 data product abstracts, that'd be over 1,000 they would have to manually review, which is quite a few. And then after we implemented few-shot prompting, the percentage of repetitive abstracts was slashed by more than half to less than 9%, which I was really happy to see that the few-shot prompting worked well. And that'll save us time in the long run for how many abstracts we will have to review manually. And we also eliminated the occurrences of the word data being considered singular within our data product descriptions.
Hey,
And for where, yes.
Sorry, we have a couple of minutes, so if you can just, like wrap up faster a little bit.
Okay, I can
We have
skip.
another session that's going to start another 15 minutes to set up. Okay, sorry.
Okay, yes, I'll wrap up. Thank you for letting me know. And so I'll skip the deployment for phase one and get straight to phase two. I don't have many details for this one, but phase two involves generating one paragraph of the description based on information from our handbooks. And as you can tell from this sample table of content, there's a lot of information in our handbooks, some of it very useful, some of it less useful. So it would be important for the user for us to summarize this into a one paragraph description. And for our context retrieval workflow, I already talked a little bit about RAG earlier. And as is normal with a RAG workflow, we have the documents, in this case the instrument handbook, chunked and stored as embeddings in a database table. However, we're adding a little bit to the RAG workflow in that we are also only searching within the relevant instrument handbook for the given data product description, since the title of the handbook is given as a metadata tag. And then within this correct handbook, a semantic similarity search is conducted to pull the most relevant chunks from the most relevant handbook. And from here, the relevant context, prompt, and query are fed to the LLM, where the final abstract is then generated. And for the prompt augmentation that we've done so far, so you can see from this prompt that the first part of the first sentence tells the model to focus on the instrument when generating text, and the second sentence tells the model that the information provided should be described as details for previously described measurements. And the similarity search is also conducted based on the prompt. So in the second sentence here, the methods and measurements tells the model to search for the most relevant chunks, relative to the methods and measurements. And then the last part of the second sentence tells the model to search for information related to the specific instrument class to ensure that the most relevant information is searched. And for the future work for phase two, work is still needed to augment the prompt to pull the most relevant chunks from the correct handbook. And for the evaluation for phase two, we will of course still evaluate the descriptions for repetitiveness and grammar. But since the handbooks are broader than the metadata information, we had a discussion earlier on Zoom that PDFs operate a lot different than CSVs. Since the PDF's handbooks are much broader, more work should be done to account for potential hallucinations, since there's a lot more extra information for the model to hallucinate on. So we also plan to evaluate the model with a different model, specifically trained on scientific data sets to reduce the possibility of hallucinations. And I don't need to read all this since we're low on time. And I'd also like to make some acknowledgments. I'd like to thank my co-authors, Hannah Collier and Dustin Rapp, for constantly keeping me on track and giving me good advice, and the machine learning group at the ARM Data Center for all their help and advice, and Franklin Perry on the ingest team for help with coding, the database team for help with setup, and the user tools team for data discovery, feature integration. And also I'd like to thank everyone here who stayed 30 minutes late to hear the presentation. I hope you all thought it was worth it. And I will now leave a QR code here, which this will take you to a feedback form. And I think I accidentally duplicated Debjani's efforts in doing that, but so you can leave a feedback form either through the form Debjani sent or this QR code. And I also left my contact information if anyone wants to send me an email later, or I'll take any questions here in the time we have left.
Thank you, Zach. That was a great presentation. So, any questions for Zach? I think, yeah, so we don't have much time for questions. However, if you all can leave questions for Zach either through this QR code, since the presentation will be available online, or through the Slido links that I have on my presentation. So you are more than welcome. Or you can reach out to Zach at his email and provide him with feedbacks on his work.
I can leave my email up for a second again.
Sure. Thanks, Zach. Thank you so much.
Yes, thank you, and thank you for giving me the opportunity to present virtually as well.
Sure, and we apologize for all the challenges that we faced, so especially you faced because of technology. Okay.
It happens.
Okay, sure. Take care. Bye.